All right, good morning, class. This is lesson 17, covering section 4.4 of our textbook. So we're continuing in this chapter 4 section where we've been discussing vector spaces, subspaces, how to find a basis for a vector space. We've seen some examples of a basis, some brief explanations for why a basis is important. But today's lecture, we're going to spend in 4.4 really diving into more about what is special about the basis. Why do we even care about a basis? And how can we use it to solve some common problems, right? So the most common thing to think about when we're talking about a basis is you're trying to design the movement system for, you can imagine like, like a little robot to traverse some kind of map, right? In fact, you can imagine like the little robots on campus that drive around carrying the food. If you've seen them going around on campus, you can imagine if you take like a map of the entire campus, take a map of the entire university campus. This is a two-dimensional map, top-down view of the school, right? And if you were to zoom in on this map, and you could see that, okay, there's sidewalks or there's paths between buildings, so on and so forth. You want your little robot to be able to deliver food to anywhere on the map. How is it supposed to figure out how to go? Well, first of all, it needs knowledge of the map, right? And secondly, it needs a way to move around. Now, for a two-dimensional map, you need a basis of two vectors, right? So in R2, we know that we can have a basis of 1, 0, and 0, 1, right? The x-axis and y-axis. This allows you to take any linear combination of these two vectors, allows you to travel anywhere in R2. Or likewise, you could travel anywhere on this map. Now, of course, the robots on campus work a little bit differently than having a basis exactly. If you've seen them move around, you'll kind of notice they have the ability to kind of rotate and pivot around. And then whenever they're facing some direction, then they can travel forward in that direction. They can travel backward in that direction. So the way that they actually work is, instead of having a basis of two vectors, they just have a single pivot where they can rotate all around 360 degrees, right? And then once they're facing whatever direction they need to move in, then they can move forward in that direction and backwards, right? That's traveling forward and backwards along some chosen vector once it's rotated enough, right? So even the program that's behind how this is working on some kind of vector equations, right? So it's one application where you can imagine. You could also see, as we've discussed, that a basis does not have to be the identity vectors, right? We like the basis of the identity vectors because on one hand, it's nice because no matter what vector you think of, it's always x times the first plus y times the second, right? These scalars don't change into any other numbers. But if I have some basis, which is something else, let's say 1, 0, 1, 2. Well, now if you want to rewrite some vector in terms of these vectors, well, now you might have to get a little bit more creative, right? C1 and C2 are some constant scalars. The point here is that when your basis is a non-identity basis, then you might have to solve for the scalars to figure out what combination of these directions allows you to go wherever you want, right? For the identity basis, you can just take those entries. You don't have to solve for the constants. and this is going to work, right? Now in practice, why does this matter? Why don't we just always use identity basis and then there's no work here, right? Well, the issue here is you can imagine, let's say, now let's talk about a lunar module, three-dimensional space, right? Your module is floating in space within the gravitational pull of the Earth, right? So it's floating somewhere between the moon and the Earth. You would like your module to be able to arrive at the moon, right? Well, okay, that's a three-dimensional space. In order to span a three-dimensional space, in order to travel to any point in a three-dimensional space, you need here we go. Now it's on the camera. You need three basis vectors, right? You need three independent directions you can travel in, right? And we did this demonstration a little bit in a previous video. In order to travel anywhere in a three-dimensional space, you need three unique directions you can move in to be able to travel in, right? If you only have two directions you can travel in, well, what I've created here, this is a plane, right? I can travel anywhere in this plane of these two directions, but with just with this blue and black direction, you can see right away just by looking at this, I can't travel up. I can't travel down. Combinations of these vectors are only going to allow me to go anywhere in the plane of these two. So in order to travel anywhere in a three-dimensional space, I need a third independent direction, right? All right. So the issue then becomes, well, when you're designing your lunar module, maybe it's not possible due to the engineering and the way that the module is designed. You can't have a vector that's going in the identity directions, right? The way that the engineers have designed it, you have a propulsion system, right? You have little jets that can turn on and off in some different directions, and that will push you in the direction of whatever vector that that little propulsion system is pointing in, right? The point we're getting at here is that in order for that to be a efficient propulsion system, those thrusters need to be pointing in three independent directions. Now, those independent directions, they may not be pointing in the identity vector directions. And if they're not pointing in the identity vector directions, well, then you need to be able to tell your astronauts, or you need to tell the engineers or the programmers, whoever's designing it, how long each thruster needs to be on for so that your module can arrive where you want it to arrive. How do you figure that out? You need to know what combination of your basis vectors is going to get you to the x, y you want to be at, right? This is really where the power of this kind of problem comes into play in terms of application, right? Now, lucky for us, we do have a theorem here that's going to help. And in part, we can see this is true because the whole point of a basis, remember our definition for a basis, there were two requirements. One, it has to be linearly independent, but two, for any basis you come up with, your space is the span of that basis, right? Remember this requirement from the last video? So long as your space is the span of the basis, that means every single vector in your space can be rewritten as a combination of your basis vector. So there's always a solution that exists for this kind of problem. We can always find out how much do I need to turn on each thruster in each direction in order to get to where I want to go. Now, okay, there could be an issue of like, well, what if your thrusters has a mechanical failure and it won't turn on anymore? Well, then possibly you just lost a vector direction, and then in which case you got to get a little bit more clever with how to solve that kind of problem. When that thing kind of happens, then you might have to rely more on outside forces, such as the gravitational pull, right? Now, of course, this is not a physics class or an astronomy class, so we're not going to go into all of that detail. For now, we're just kind of solving these problems based on the basis idea. Of course, in reality, other things can happen, other problems can happen, mechanical failures can occur, but we're not gonna deal with that in this class. Okay, so what's this theorem? Well, we already know, based on this fact, that when you have a basis, that means every vector can be written as a combination of the basis vectors. So that's exactly what this theorem says. This is called the unique representation theorem. The unique representation theorem. All right, so if script B, right, remember using this fancy B for a basis, this is going to equal B1, B2, dot, 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 Bn. So suppose that B is a basis for a vector space, vector, if I can spell correctly, space capital V. Then what does this mean? Well, because it's a basis for the space, that means this space equals the span of this basis vector. So for any vector x in V, we have there exists, not only is there a solution, but it's a unique solution. Why? These vectors are linearly independent. So we don't have free variables, which means we don't have multiple solutions. There's only one unique solution. There exists unique scalars, C1, C2, dot, 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 Cn, such that what happens, x is a combination, a linear combination of my basis vectors. Right? This can always be done because, one, a space is the span of its basis vector. So a combination exists, but that combination is only one combination. There's only one solution. There's only one set of scalars that works because my basis vectors are linearly independent. There are no free variables, so it's impossible to have multiple solutions here. There's only one unique solution. Now we have a special name for this solution. The B coordinate, whoops, if I can spell. Spelling is tricky. Coordinates of x is the vector, or rather is a vector comprised of the scalars C1, C2, dot, 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 Cn, right? So we use this notation where we have x in brackets with subscript b. This is saying x in terms of this basis b. Or in other words, this vector rewritten as a combination of the basis b. This is saying, what are those scalars that makes the linear combination happen? We're going to take those scalars and make them a column vector. This is the solution to that application problem we're discussing. This is telling you how much each thruster in each direction has to be turned on in order to arrive where you're trying to arrive, right? So this is the solution. This is finding what those scalars are. Now in practice, how do we actually find the scalars? Well, look what we're doing here. Look what's happening here. This is just a linear combination, right? And we know all linear combinations can be rewritten as matrix multiplication, where I'm taking my basis vectors and they're getting multiplied by scalars. And we want this linear combination to result in x. In other words, what's happening here? We're taking a matrix of our basis vectors, and what we're solving for now is the b coordinates of x, right? We're solving for x in terms of b, x in terms of the basis here, right? So how do we actually solve this problem in practice? Well, we know how to solve this problem in practice. This is a matrix equation. This means take a matrix of your basis vectors, augment with x, row reduce and solve, and you're going to find the solution. You're going to find what scalars make it happen. The scalars then create our basis vector, our b coordinates of x in terms of the basis, right? Now, sometimes, depending on what your basis is, this is an easy, trivial problem. So, for example, we can think about, let's see, I'm going to leave this stuff at the bottom, but I'm going to erase what we have up top, since the bottom is going to give us the idea for what we're actually trying to solve here. All right. Now, as we've already noted, something special happens when our basis is comprised of the identity vectors. Let's let B1 equal the basis of identity vectors for R2, right? This is a basis for R2, right? We already know this. Okay, and then let X equal 1, 2 in R2. Okay, so we could ask the question, what is X in terms of this basis? How do we solve that question? This is the same thing as saying, all right, we want to find out what are the scalars, what is the linear combination of the first basis vector and the second basis vector that results in X. But this question, this is a linear combination. This can be rewritten as matrix multiplication. Can be rewritten like this, right? Where X is this vector 1, 2, right? Now, lucky for us, we already know the solution here, because what happens, well, I can just take my entries in X. This is 1 in the x-axis direction plus 2 in the y-axis direction. In other words, my X in terms of this basis is just the same vector. And in fact, this is something that's going to happen every time when your basis is made up of identity vectors. Now, we do have to be very careful here. Why do we have to be careful here? Because the order of your basis vectors matters, right? The order in which your basis vectors exist, that's the order you're creating your matrix in, right? Whatever order they're given to in your basis, that's how you're creating your linear combination. So if I just make this simple change of, well, what if I make some other basis, I'll call it B2, where I swap the order of my identity vectors, right? And now we can rinse and repeat, do the same problem. And now this is 2 times 0, 1 plus 1 times 1, 0. But this is my C1. This is my C2, right? The order in which I take my linear combinations, that's giving me the order of my scalars. That's giving me the order of my B coordinate vector, right? In other words, x in terms of this B2 basis, the B2 coordinates of x is now instead 2, 1. So what happened in this? Well, now it's no longer the same vector. It swapped my x and y. Why did it swap the x and y? Because I swapped my x and y axis. That's what this basis is doing. This basis is swapping your x and y axis. And if you swap your x and y axis, then you're inevitably going to end up swapping your x and y. All right. The point I'm getting at is you want to be very careful about the order in which these are written. Make sure you use the same order when you're trying to do your linear combination. And that's going to be important in order to solve these problems correctly. Okay. But now let's talk about a little bit of a trickier example where maybe I'm not going to use identity vectors in my basis. Then what do we do? All right. Well, what if instead we still have the x-axis, but now my second vector is 1, 2. All right. Now this is still a basis for R2. Notably, first of all, they are linearly independent, so that's good. And secondly, because they're linearly independent, I have 2 pivots, which means if I take a linear combination of these 2 vectors, that's going to be enough to travel anywhere in R2 because I have 2 pivots. Okay, so this is a basis. But now, when x is, again, let's just leave it as 1, 2. What is x in terms of this basis? How do we find out? Well, we know from what we've already done, this is the same question as asking what scalars, what linear combination of my basis vectors is going to result in this x, right? This is the same question. I want to find these scalars. How do I find them? I take my matrix and I'm going to augment with x. And we have 1, 0, 1, 2, 1, 2. Now, lucky for us, this is already in a echelon form. I can go ahead and start solving. So if I look at the second row of this matrix, we see that we have 2 C2 equals 2. In other words, C2 equals 1. Okay, what about C1? C1 equals 1 minus, if I subtract this over, I have negative 1 times C2. Let's give me C1 equals 1 minus 1. C1 is 0. In other words, my x rewritten in terms of this basis is 0, 1. So again, notice, depending on what your basis is, and in fact, when your basis is not the identity vectors, your B coordinate vector of x, or in other words, your x rewritten in terms of that basis, is going to be a different vector than what you originally started with. What we're solving for here is this is answering the question, how much do I have to travel in each direction in order to reach 1, 2? Well, what's funny about this example is what is our answer saying? Well, because 1, 2 is one of the basis vectors, in order to reach 1, 2, all I have to do is travel 1 unit in the 1, 2 direction. So you can imagine, let me draw a picture. We have a vector going in the x-axis direction. This is 1, 0. And then we have a vector going in the 1, 2 direction. So this is something like this, right? This is my basis. These are two independent directions, which means if I go in a negative direction, or if I go in a negative direction for the other, these two vectors together, I can take any combination of these two vectors and arrive at any xy on this plane that I want. But in particular, if I want to arrive at 1, 2, then what does this say? This says travel 1 unit in this direction, this 1, 2 direction, and you will arrive, right? Now, the funny thing about what we're doing here is this is the same thing as designing a coordinate system, right? In fact, this is the coordinate system that you learned in elementary school when you first started graphing. Except, what was it you were doing? Well, you were using the x and y axis, right? When you first learned about coordinate systems in elementary school or middle school, whenever you learned it, you were taught you can travel in the x-axis direction, x-axis, or the y-axis direction. And when your teacher said, like, okay, how do we get some point which is at xy? We said, well, you travel x units along the x-axis direction, and then you're going to travel up y units in the y-axis direction. What you were doing was you were finding the b coordinate vector of x. You were saying, how do I get to x given this basis? Well, it just so happens when your basis was the identity basis, the basis of identity vectors, that it's the same vector, right? So you've been doing this basis coordinate system all along ever since middle school. It's just your teachers never told you this is what you were doing. But in fact, it's the same thing, right? What's different now is, well, what if I take a basis which is not the friendly and simple x and y axis, where it's not the identity basis vectors? Well, this still works. It just, now you actually have to solve for how much do you travel for it in each direction, right? Now you actually have to solve for what combination of these directions can get you to some vector x, y. And in practice, this is where the robot application comes back in, right? You could design a robot where maybe a robot can only move in 2 directions, right? It's a little bit limited. You don't have the ability to rotate or pivot the robot, but it can walk in 2 different directions. You want to know, okay, how much does it have to walk in each direction in order to arrive where you want it to? That is exactly what this question is solving, what this application is for. Okay. So let me also write out some other notation that can be helpful here, make things a little bit clearer. And we'll also do some other examples. All right. So first of all, we've already hinted at this a few times, but something special happens when the basis is comprised of the identity vectors, the identity column vectors. So a basis comprised of the column vectors from the identity matrix. A basis comprised of the identity matrix column vectors is called a standard basis. Why is it called standard? Because that's the basis you first learn in elementary school. This is the basis you learn for how to graph things, how to plot points on the XY plane. This is the basis that is most intuitive, that is the easiest for plotting points without having to think too much about it, right? Now, if we let the Greek letter epsilon be a standard basis, so if epsilon is a standard basis, then when we try to find x in terms of this standard basis, it is always just x again. So if you run into problems where they're asking you to find the basis coordinate vector of x, if the basis is a standard basis, well, then your answer is just the original vector x. You don't have to solve anything. You don't have to calculate anything, right? So this is a nifty trick we can use, but this only works when the basis is the standard basis. When it is not the standard basis, well, then we have to do a little bit of work. How do we do that work? Well, again, like almost everything in this class, it comes down to examining some kind of augmented matrix and correctly row reducing that matrix. All right, so we have in general, let B be some basis with B1, B2, Bn. It doesn't matter how many vectors are in the spaces, although it'll always be finite in this class. Again, recall that we've discussed we're only going to deal with finite dimensional things in this class. If you take more advanced linear algebra courses or some other advanced physics courses, then you may be considering some infinite dimensional cases, but not in this class. All right, then what? Well, we already have created this matrix equation earlier. If I create a matrix of my basis vectors, and I want to take a combination of my basis vectors, I want to know what combination of my basis vectors can equal x. Now, the textbook does introduce some notation here. And at first, this notation might be a little bit weird. You might be asking, why are we using this notation? That will become more apparent when we come later into chapter 5. This notation is going to be very useful for some other things we're going to do. But for now, let's just go with it, and we'll see later in the course why this notation is helpful. So I'm going to use capital P sub B. This is going to be the matrix which is constructed from my basis vectors. Okay? Then what can we write? Well, then we can write PB times x in terms of B equals x. So we have lots of ways for solving this kind of matrix equation, right? As we've done previously, we always know you can take this matrix PB, augment it with what you want it to be equal to, row reduce and solve. You can find the scalars, right? But alternatively, what else can we do? Well, notice these vectors are linearly independent. So if this matrix is also square, right? If PB is square, which it won't always be square. Oftentimes for the problems and examples we look at, it will be square, but this matrix does not always have to be square. That's why I'm putting this caveat here. If it is a square matrix, then it's linearly independent, therefore it's invertible. Well, now all our invertibility stuff from chapter 2 kicks in. And what do we have? I can multiply by the inverse matrix on the left. In other words, another way to find the B coordinate vector is to multiply by PB inverse times x, right? This is an alternative way to solve this question. So another way of thinking of this is that PB you could treat as the standard matrix for a transformation, right? So if T is a transformation with PB as its standard matrix, right? That means you plug in a vector x, it gets multiplied by PB, that is going to output a new vector as its standard matrix, then T transforms the B coordinate vectors back into their original X, into the original X vector, right? So you can use this matrix multiplication here for what if instead they give you the B coordinate vector of X and they want to know the original X. How do you find it? Well, then you got to do matrix multiplication here. This is a transformation from the B coordinate vector into X. But vice versa, if T inverse is a transformation blah, 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 with PB inverse as its standard matrix, so now we're thinking about this picture up here, then T inverse transforms X vectors into the B coordinate vector. So part of the power here I'm getting at is depending on which one you're trying to find. Are you trying to find the B coordinate vector of X? Or are you trying to find the original vector X? Depending on which direction you're trying to go, either equation can help you solve that kind of question, right? So I want to do one more example, and then we'll call it a day here. So now, just to really drive home the point, let's again think about the situation when, where'd my marker go? Oh, that's strange. Where does, oh, there it is. It's under my keyboard. All right. Let's think about the case where, let's say 1, 0, 1, 2 is our basis. Now, for the sake of this lesson, I've been doing all these examples in the two-dimensional case. If you're working in R3, R4, R5, you solve this problem the exact same way, right? You create an augmented matrix, row reduce, solve for your scalars, right? It's the same old problem we've been solving this entire summer class, right? All that's new is that we're attaching new vocabulary to what it means to solve these kind of problems, right? So we can understand other applications for where these matrix equations can be helpful. Okay, so if it was 3 vectors, 4 vectors, 5 vectors, doesn't matter how many vectors are in this basis, you're always going to solve this problem the exact same way. Now, let's let X be something a little bit trickier. Let's say it is 3, 4, right? And I want to find X in terms of this basis. And actually, you know what? Let me make it a little bit trickier. Let me say 1, 1. That way, they're not already in echelon form, and we actually have to reduce something here, okay? So my basis vector is 1, 1, 1, 2. Note, these vectors are linearly independent. They are not multiples. Therefore, I have 2 pivots if I reduce them. And we're going to find that because they're linearly independent and I have 2 pivots, then R2 is the span of these 2 vectors, right? So a solution does exist, right? The B coordinate vector of X does exist. Now we just have to find it. How do we find it? Well, it's the same thing as take my basis vectors. I want to know what combination of them is going to result in 3, 4. Well, to solve this, we know we need an augmented matrix. Also, alternatively, based on what we just had on the board a second ago, sure, you could try to find the inverse of this matrix and then multiply both sides by the inverse. In fact, that could be just as fast. But I'm going to solve it both ways just so that you can see how it works. So suppose you try to solve it this way first, where you augment the matrix, row reduce. Is kind of like the standard way of solving these kind of problems. Well, I'm going to subtract row 1 from row 2, and we're going to get this, right? So this is now an echelon form, which is enough to get my solution. I saw in the midterms, a lot of students, they keep trying to reduce the matrix all the way to reduced echelon form, which is fine if you want to do that. But in all honesty, sometimes trying to go all the way to reduced echelon form can get very, very messy with fractions and decimals. And honestly, it's just not worth the headache. Getting to echelon form is enough to answer the question. Why? Because I have a pivot for each variable. This already tells me everything I need to know. What does this say? Well, C2 equals 1. What about C1? Well, this is the equation C1 plus C2 equals 3. In other words, C1 equals 3 minus C2, which is 1. So C1 is 2. In other words, my B coordinate vector of X is the new column vector, 1, 2. Now, what is this saying? It's saying, wait, hold on. Did I write this correctly? 1, 1, 1, 2, 3, 4. Oh, yeah, we're fine. Okay, this is good. Oh, I flipped it here. That's why it looks weird. C1 is 2. Yeah, make sure you have things in the correct order. It does matter. What is this saying? The point of this solution is saying, well, if you travel 2 in the 1, 1 direction, 2 times 1, 1, and then travel 1 in a 1, 2 direction, that is going to arrive at, where is it going to arrive? Well, 2 plus 1 is 3. 2 plus 2 is 4. That will arrive at 3, 4. This is telling you how much to travel in this direction, how much to travel in this direction to arrive here. That's what we have solved here. That is the answer we have questioned, or the question we have answered. Alternatively, what if instead, let's treat this as my matrix A, or actually, let's stick with the same notation we've been using. This is the matrix PB. Instead, I could try to find PB inverse. All right, well, I need 1 divided by its determinant. 1 times 2 is 2. Minus 1 is 1. Lucky for us, the determinant is 1. Swap the diagonal. Apply negatives to the off diagonal. So all that inverse stuff we learned in chapter 2 is still relevant here in chapter 4. My inverse matrix is 2, 1, negative 1, negative 1. Well, what's the point of this? Well, if I multiply both sides by the inverse matrix, we have PB inverse times X is going to equal my B coordinate vector. Well, that's 2, negative 1, negative 1, 1, times my X, which is 3, 4. And what do we get here? Well, 3 times 2 is 6. Minus 4 is 2. 3 times negative 1 is negative 3. Again, what am I doing here? This is the dot product, right? That dot product for matrix multiplication, super crucial. We're going to use it forever and always in this class. Negative 1 times 3 is negative 3. Plus 4 is 1. Lo and behold, we get the same answer. So you can solve this question however you like, or using either methodology, and it's going to work. Is either one necessarily faster than the other? It depends on how big your matrix is, right? If your matrix is a 3 by 3 or a 4 by 4 or a 5 by 5, trying to find the inverse matrix might be a lot of work, right? You'd have to use that Cramer's rule formula, or you have to create a giant matrix augmented with the identity matrix and row reduce. The bigger the matrix gets, the more work it takes to find the inverse matrix. But this row reduction method, this is generally a tried and true method, which is always going to work. But again, either methodology is fine here. But also highlight here, This inverse method only works if PB is square. If you do not have however many entries and the same number of vectors, then it is not going to be square. It will not be invertible. So there are times when this might be the only way to solve the question. All right. Okay. So that is everything for today's lecture covering section 4.4. If you have any questions, by all means, please do email me. Office hours are still Tuesdays and Thursdays at 6 p.m. The Zoom link for that is on Canvas. I've also started grading the midterms. I should finish that later this week, so I apologize for the delay, but that will be done relatively soon. Okay, all right. That's all for today. Best of luck, and I will see you tomorrow.